Hi everyone, my name is Julia Murgia and I'm an undergrad student from Caltech, and I'm presenting a poster on guiding generative diffusion models with physics-informed classifiers. And so this is in the context of creating a large data set of galaxies using diffusion models for weak lensing studies. And so the problem is that diffusion models don't integrate any scientific constraints in the process. So my proposed solution is to train a classifier in identifying whether a sample satisfies a particular physics constraint that we want to implement. And so, for example, here I trained the classifier to figure out whether the image is a right triangles or not. And so what happens is that at each phase of the backward diffusion model, we apply the classifier and determine whether we are going in the right direction. For example, in this case, if we are generating a right triangles. And so the next step will be apply this to galaxies. And in this case, the constraint will become a morphology or a color constraint. So yeah, just feel free to talk to me if you're interested. I'll be around, and thank you.
Hi everyone, my name is Grant Mers. I'm a fourth-year graduate student at the University of Illinois, Urbana-Champaign. So the motivation for this project is that redshift measurements will be crucial for many different science studies that we want to do with LSST, from things like cosmology to galaxy clustering and evolution studies. But due to just nowhere near complete spectroscopic coverage of the LSST footprint, we need to somehow estimate redshifts of the observed objects. And so this motivates photometric redshift estimation. So the photometry is basically just a coarse sampled SED. And so typically this can be done, or traditionally this can be done through things like template fitting methods. So you have some sort of library of template SEDs that you can fit using some forward model of the observed photometry. Or you can use machine learning methods, so basically learn a mapping from this photometric space to the redshift. There's been an increase in focus on image-based methods. So these are basically going straight to the pixel level and using something like a convolutional neural network, or in this study we use a vision transformer-based network to basically learn that mapping from just the pixel space directly to an object's redshift. And so we did a comparison study using simulated LSST data with our network deep disk, compared it to different photometric redshift estimation methods. So come talk to me about this project. Happy to describe it more.
Hi everyone, I'm Aiden Barris. I'm a third-year PhD student at the University of Illinois. And my project is benchmarking Galaxy D blenders with the blending toolkit. So blending is a big source of uncertainty and will be for LSST images. And so a lot of people have made a bunch of different algorithms to solve this uncertainty. And so I'm here to put them to the test and see how well do they perform under different certain situations, like how close the blending is, different brightnesses, number of sources just in an image. And we can evaluate over different kind of metrics, like how well it can actually detect each galaxy in an image, how well they can segment, and how well can they perform reconstruction, where they can actually separate the galaxies into their individual images. This is to inform future development and to try to improve current blenders. So please come talk to me about this work, and you can see some performance evaluations and some outputs right here. So, thank you.
Hello, everyone. I'm Yash Ijigiri. I'm a post-bac research associate working with Grant and Professor Shin-Lu at the University of Illinois Urbana-Champaign. And so my work is also helping to solve the blending issue in ground-based surveys, because they introduce a lot of systemic biases that affect critical cosmological analyses like weak lensing, photometric redshift, and shape measurements. And so my work is essentially using the Roman Space Telescope because there exists around 20 square degrees of overlap between the Roman Space Telescope data and the LSST data. And so my work is basically combining these two data formats and improving deep disk's performance, which is, as Grant described, a source detector, classifier, and deblender using primarily vision transformers, and increase the performance harnessing the power of multi-survey data with ML-driven analysis. So my poster is down the hall into the smaller room over there, so come talk to me. All right, thank you.
Hi again. So that's me. Basically, I've been thinking of and I've been working on basically forward modeling in everything galaxies. So if you're interested, please talk to me about that. So one of the things that I probably want to mention here is that when you try to infer galaxy properties, you have degeneracies in the spectral energy distribution, so try and solve that, we think that when we try to infer them at a population level, we can sort of build in sort of nice things into that model that will help break some of these degeneracies. And so if you're interested in that, please come talk to me. Empirical form models, that's a funny thing. That's when you try to infer 3D structures out of galaxies. But we've heard many things about good priors for galaxies as well. Anyway, all right, thank you.
Hi everyone, my name is Vikram. I'm a fourth year undergrad at UCLA. My co-presenter had to step out for a moment, but that's Srinath. So the project we're working on is trying to improve the generalizability of photometric redshift prediction models. So traditionally, these models are trained on these neural network models are trained on spectroscopic redshift, and those are, I guess, biased towards strong emission line galaxies, and so these models don't generalize well across galaxy populations. And so we made a new data set which consists of a photometric redshift catalog, and so we're hoping this is a more representative galaxy population. And so we wanted to leverage both the accuracy of these spectroscopic redshifts and the representativeness of photometric redshift catalogs together. And so we evaluated methods of like mixing these ground truths in training convolutional neural network models. Our model itself was a ResNet with a linear classifier. And we combined the ground truths both by simply combining both data sets in training, so that's the combo model, and then also using a method called low rank adaptation, which is usually used for LLMs to fine tune them. And essentially we find that at the moment, like these methods of mixing ground truths, apart from just combining them directly, doesn't perform as well. However, there are a lot of like computational advantages in methods like low rank adaptation and other transfer learning methodologies that are advantageous. So if you're interested in photometric redshift prediction and I guess improving the generalizability of these models, you can come to our poster, which is down the hall next to the terrace. Thank you.